Today we are going to start unit 2, and this is the lecture number 1 of our course heat and mass transfer. Okay, so the first topic in the unit 2 is the derivation, is the understanding what is generalized thermal resistance network. Unit 1 is started with the basic concept of basic concepts of heat conduction. We are still it ended after we derived the equation of heat conduction, general equation of heat conduction, and we moved forward and we derived a transient heat conduction equation. So now in this unit we will deal with the concept of generalized thermal resistance network. So the objectives of this lecture are to develop the intuitive understanding of thermal contact resistance and some circumstances under which it may be significant. Identify the applications in which insulation may actually increase heat transfer. Analyze the fringe surfaces, assess how effectively and efficiently fins can enhance heat transfer, solve multidimensional practical heat transfer conduction problem using conduction safe factor. Okay, so these are our objectives. So we will start with the by be, I mean we will start with generalized thermal resistance network. Okay, as you can see, as we have discussed in the previous unit, the last lecture of previous unit, that heat transfer, if let us say this is the you can say composite or cylinder wall, where these are two layers. Layer 1 has thermal conductivity K1 and layer 2 has thermal conductivity K2, and this is the insulation that has been provided over here. And if length L is the length, and the temperature on this side is maintained at T1 and the temperature on this side is maintained at T2, and these are the areas of the respective layer. Layer 1 has area A1, layer 2 has area A2. So this can be replaced by a you can say by a thermal resistance network for two parallel layer. Okay, so this is analogous to the electrical resistance. Okay, so what we will do, we can replace the whole system with this circuit. Okay, where R1 is the thermal resistance of offered by the layer 1 and R2 is the thermal resistance offered by the layer 2. Okay, so if this kind of condition exists, then we can replace this whole system like this electrical circuit. Okay, and the heat transfer, as you can see, since heat is entering at the rate of Q, so it will be divided into two parts, a Q1 plus Q2, and so Q equal to Q1 plus Q2, and it will leave as a Q and at the surface which is maintained at a temperature of T2. The total heat transfer is basically Q, and it is can be divided into two parts, Q1 plus Q2. And so we can write in the place of Q1 as T1 minus T2 upon R1. R1 is the thermal resistance. We have discussed what is the meaning of thermal resistance in the previous unit, and this is R2 is the thermal resistance offered by the T2. This is equal to T1 minus T2 into 1 upon R1 plus R2, and the final equation will be like this one. Okay, like Q dot equal to T1 minus T2 upon R total, and if we compare this R total with this one. Okay, so what we find? We find that 1 upon R total equal to 1 upon R1 plus R2. So we can say R total equal to R1 plus R2 upon R1 plus R2, R1 into R2 upon R1 plus R2. Okay, so this is how the you can see. If this kind of situation exists, then these are called the thermal resistances in parallel. It is similar to the thermal resistance in electrical circuit. Now consider this one more case where these three layers of the materials. Three different materials are arranged in this way. Okay, so what is the and now you can see 1 and 2 are in parallel like in this previous case, but R3 is not parallel. It is in fact positioned in this way. Okay, so what is the total resistance? Total resistance will be R1 to R3 plus R conventional R convection heat transfer. Why R convection? Because this side opens to a medium where heat conduction coefficient is H, and which is maintained at T infinity. T infinity means the temperature of the atmosphere. Okay, and you can see the length of these two is repeat. L1 is equal to L2 and this part is L3. So this system, whole system can be replaced by this circuit. Okay, as you can see R1 and R2 are in parallel. Okay, so R1 and R2 will be in the parallel, then R3 will be in the series to this circuit, then this is R convection. Okay, and this end is maintained as you can say ambient temperature T infinity. Okay, so this is the thermal resistance network for the combination of series and parallel network. Okay, so you can see R1 is L1 upon this is the value of R1, this is the value of R2, this is R3, and this is R convection. Okay, so there are two assumptions in solving a complex multidimensional heat transfer problem by treating them as one dimensional using thermal resistance network, and these assumptions are any plane will be normal to x-axis, is isothermal, that is to assume this temperature of any in x direction only. Any plane parallel to x-axis is adiabatic, that is to assume that the heat transfer to occur in any x direction only. Okay, so this is the assumption that is taken for the derivation for the derivation in this kind of problem. Okay, so heat conduction in cylinders and you can say is fair. Heat conduction through the pipes can be modeled at steady and one dimensional. The temperature of the pipe depends on one direction only, the radial direction, and can be expressed as T equal to TR. Temperature is independent of the azimuthal angle or the axial distance. This situation is approximated in practice in long cylinder pipes and spherical pipes. As we can see in this figure, it is lost from the hot water pipe to the air outside in the radial direction, and thus heat transfer from a long pipe is one dimensional only. Then the heat conduction in the cylinder and sphere, we have derived this equation for the one dimension, q equal to minus ka dt over dr, and after this is the different in we have derived this equation in the differential form. Okay, so if we integrate this equation from r1 to r2, if you see from the figure, then what we will get? We will get this equation. This is the equation that we will get after integrating. Okay, so heat conduction equal to 2 pi Lk T1 minus T2 upon ln R2 upon R1. Okay, so again, if we utilize the heat resistance analogy, then heat conduction through the cylinder can be written like this, and if it is written like this, then we will see that the resistance offered by the cylinder is given by this relationship. Okay, this is the relationship that can be used to find the resistance offered in the conduction of heat by a cylinder. Okay, so this is the equation that we will get. Then again, in the case of sphere, we will this kind of formula will be found out by, and this formula will be found out by integrating the heat conduction equation that we discussed in unit 1. Okay, so the heat resistance can be obtained like this, where R2 minus R1 upon 4 pi R1 R2 into K. Okay, R2 is the outer radius, R1 is the inner radius, and K is the thermal conductivity. Okay, so this is the thermal resistance that can be calculated using by using thermal resistance analogy. Okay, and this R is called the conduction resistance also. So the thermal resistance network for the cylindrical or spherical cell, as we can see, if there are more than one cylindrical layer over another cylindrical layer, so obviously those these layer will form some sort of thermal resistance network. Okay, so let us consider this example. Okay, where this is the cylinder and this is the inner cylinder. Okay, it has some, it may be solid or it may be hollow and having some, you can say, some material inside it or some fluid inside it. Okay, so thermal resistance network for a cylindrical or spherical cell subject to convection from both an inner and outer side. Okay, so in this case, what is happening, that from inside the heat transfer is due to the convection, and from outer side again the heat transfer is due to the convection, and this is the solid body part where the conduction will take place. Okay, so how the thermal resistance network will be made, that some resistance will be offered in the convection, then some resistance will be offered as conduction resistance by the cylindrical body, and then some convection resistance will be offered of the outside area. Okay, so the at the center temperature is T infinity 1, and at this point the temperature is T1, and at this point the temperature is T2, and the atmospheric temperature is T infinity 2. Okay, so the total resistance is resistance due to convection at inside, and then resistance offered by the cylinder, and the resistance offered by the convection of the outside of the cylinder. Okay, so the total resistance, as you can see from the figure itself, will be equal to this value. Okay, try to derive this equation at your home, and you will encounter this kind of equation. Similarly, for the sphere, same in the similar condition, and in case of sphere, this kind of equation will be obtained. Okay, so this is the equation that we will get if we utilize the thermal resistance network for the cylinder, and find after calculating the thermal resistance of the cylinder, it becomes very easy to calculate the heat transfer rate from the one part to another part of the body. Now let us consider the this multi-layer cylinder and spheres. Okay, so if there are multiple type of layers, then how we will calculate? Okay, for example, in the cylindrical case, if there are many layers, this is the layer 1, this is the layer 2, this is the layer 3. So all these three layers are metallic, and inside the temperature heat transfer is due to the convection, and outside again the heat transfer is due to the conduction. So again we will, what we will do, this is the thermal resistance. Okay, due to the convection, then the cylindrical part, then cylinder 2, then cylinder 3, and then again heat resistance due to convection. Okay, so the thermal resistance network for heat transfer through a three-layered composite cylinder subjected to convection on both sides. Okay, so this is the circuit which is shown here. As you can see, it is very clear from the figure that if we are able to make this kind of you can say this kind of figure, then solving the problem becomes easy. And one interesting thing is that along this circuit, q is constant, so we can easily identify what are these temperatures, T1, T2, T3, T4, all these intermediate temperature, if we utilize the thermal resistance analogy. Okay, that is why it becomes very important. So again in this case, this is the again I mean, this is general, it is written over here, the what we have discussed here, that since heat transfer rate is constant, so heat transfer can be easily calculated using these relation. All these relation we can find out what if we have calculated the heat transfer rate, then we can find all the other all intermediate temperature within the body. Okay, so the ratio delta T upon R across any layer is equal to Q, which remains constant in one dimensional steady conduction. Once the heat transfer rate Q has been calculated, the interface temperature T2 can be calculated from any of the two following relation, as we can see from here. So this is what we have discussed, and let us move to the slide. the critical radius of insulation. This is one of the most important, one of the you can say the topic of interest of the engineer, where we have to calculate what is the required or critical radius of insulation. Okay, so adding one more insulation on a wall or to the attic always decrease heat transfer, since heat transfer area is constant, and adding insulation always increases the thermal resistance of the wall without increasing the convection resistance. In a cylindrical pipe or a spherical shell, the additional insulation increases the conduction resistance of the insulation layer but decreases the convection resistance of the surface because of the increase in the outer surface area for convection. The heat transfer from the pipe may vary, may increase or decrease depending upon which effect is dominant. Okay, so in cylindrical case, sometimes what happens that when we add insulation, it may happen that the heat transfer rate from the cylinder or sphere may increase or decrease, while in the case of walls or plain wall, the heat by adding insulation, the heat by adding insulation, uh, the addition of insulation means there is always a decrease of heat transfer. But in case of you can see the cylindrical or spherical bodies, this is not the case. Adding insulation may increase or decrease the you can see I mean may increase or decrease the heat transfer from the body. Okay, this happens because due to conduction resistance increases but the convection resistance or I mean the conduction resistance increases but the convection resistance reduces. Okay, so one of the effect may get maybe more prominent while adding insulation. Okay, so insulation doesn't mean in case of cylindrical bodies, insulation doesn't mean that there is a increase there is a decrease in the heat transfer rate. Adding insulation on cylindrical or spherical shell may result in an increased heat transfer rate. Okay, so we have to see whether how much insulation we should add, that I mean we have to look if our purpose is we have to find out how much insulation we should add. Okay, so if let us say this is the a cylindrical body and on which this insulation is added. Okay, so if we look if we utilize the thermal resistance network analogy over here, we can say that heat transfer rate is T1 minus T infinity upon R insulation plus R due to convection. By adding we have essence we have added insulation, so the convection heat transfer will be prominent. Okay, so this is the formula that we will get after the addition of insulation. So for the cylindrical surfaces, the critical radius for insulation for cylindrical body is calculated using this formula. Okay, so if the thickness of the insulation or the radius is less than the critical radius, then the addition of insulation will always result in an increased heat transfer. Okay, so if we want to reduce the heat transfer, we have to add insulation which is more than the critical radius of insulation. Similarly, for the case of a sphere, this is the relationship that should be utilized to find out what is the critical radius of insulation. Okay, so these are the two relations that can be utilized to find out what is the critical radius of insulation. Okay, if the critical radius of the insulation is if you are adding less in insulation and the critical which is less than the critical radius of insulation, then there is always an increase in the heat transfer rate, as we can see from this figure itself. Okay, that when the radius was R1, this was the heat transfer. Okay, after adding some insulation, let's say we have added some insulation, so the radius was increased to this value. Okay, and after doing this, some heat transfer increased. Okay, but as soon as we added the heat insulation up to the critical radius, the heat transfer rate became maximum. Okay, beyond adding, I mean, one if we have added one more layer of the insulation, then what happened, that the heat transfer rate kept on decreasing. This is how the heat transfer rate varies with critical you can say with the thickness of insulation. Okay, so the largest value of critical radius we likely encounter is the K max of the insulation upon H minimum, which is equal to 1 centimeter. So we can insulate hot water steam pipe freely without worrying about the possibility of increasing the heat transfer by insulating the pipe. So heat transfer from the finned surface. Okay, as we have seen in many of our home appliances, that sometimes we add some you can say some sort of fins, or some sort of you can say extra fin type of material on the surface to increase the heat transfer rate. Okay, so the from the Newton's law of cooling, we know that heat transfer from by the convection is given using this formula. Okay, where Ts and T infinity are fixed. Two ways to increase the heat transfer rate. First way is to increase the convection heat transfer coefficient H. This may require the installation of a pump or a fan, or replacing the existing one with larger one, but this approach may or may not be practical. Besides, it may not be adequate. Okay, so the other way is that to increase the surface area by attaching some extended surfaces. These extended surfaces are called fin and made of highly conductive material. These fins are made from highly conductive material such as aluminium, and that is why these are used for the heat transfer, mostly in the in the refrigerators, in the air conditioner, or these you have seen many finned surfaces, and the purpose of those finned surfaces is to increase the heat transfer rate. Okay, so these are the some of the example. Thin plate fin of a car radiator. You can this is the car radiator, and to the heat transfer of air. Okay, so you can see some these extended surfaces that are you see on the dinosaur body have actually worked as fins to remove extra heat that was generated within the body. Okay, so these are the again this is the yeah, thin plates fin of car radiator that is used to remove the extra heat from the body of the car. So the summary of the present lecture is that today we studied the concept of thermal contact resistance, and we identified the generalized thermal resistance network. We calculated I mean we derived the equation, and we also identified the generalized thermal resistance network. Then we developed the general thermal resistance network for the cylinder and the sphere, and then we discussed the meaning of critical radius of insulation. This is one of the most important topic today, and we will continue with this topic in the next classes as well. So these are the review question that you can go through, and these review question, as we can see from the figure, from these question, they are simple. So the first question is, how does the science of heat transfer differ from the science of thermodynamics? We have discussed earlier, but I am giving you as a review question so that you can revisit the first unit. Similarly, define work and explain the forms of work. Again, this is the first unit, and then differentiate between heat and work. Okay, so these are the review question that we go through. This is the you can see this is the mm, fundamental of these are the reference book that you can refer to for the uh, further reading. Thank you for the time, and thank you all.